What's cracking, guys? In this video I'm covering Make a Video from Meta, a very cool novel text to video model. And in general, over the last months, we've seen an explosion in the multimodal research. So other than the text-to-image models such as DALL-E 2, Midjourney, Stable Diffusion, etc., we've seen models that do text-to-audio, models that do text-to-3D shapes, models that do text-to-video. Guys, before we continue, I want to make a huge shout-out to Weights and Biases and thank them for sponsoring the video. They're an amazing ML platform for tracking experiments, doing dataset versioning, model management, and much more. Signing up is as simple as literally typing in a couple of lines of code. And I want to show you one very powerful feature of Weights and Biases, and that's creating these powerful multi-media rich reports. So you can see how you can embed a video here, and if you click on this particular link, you end up seeing a run that produced those images. Other than just producing cool videos and images, you can interact with the plots, as you can see here. So you can see how you have a pop-up and actual numbers being displayed. And if you're a power user, you literally have unlimited flexibility. You can generate plots, bar charts, videos. You can interact with your plots, and that's very cool. So having said all of that, there is no reason why you shouldn't check them out because they are completely free for personal use and academic teams, and they have great plans for enterprises. So if you want to support the channel, sign up using the link down below. And now let's get back to the video. So this is not the first paper that's been doing obviously this task. So we had previous baselines such as cog video, such as video diffusion models, etc. But this is the one that kind of made it impressive. The first one that has really exciting results. So yeah, also there is a concurrent work, I think it was called Fenaki or something, that also has fascinating results, but I'm going to focus on make a video in this one. So you can see some of the videos generated here. And if I open up the actual landing page here, we can see the associated prompts. So let's focus on some of them. So we can see here a dog wearing a superhero outfit with red cape flying through the sky. Obviously the video is kind of weird, but it's damn impressive. So this is the first paper that achieved results such as this. So I think it's fairly laudable. So here they show some examples of three categories like surreal. So you can see here a teddy bear painting a portrait. So you can see how it looks like. You can see the hands are kind of weird or something, but it's amazing that the model even had the imagination to generate a content like this. So that's kind of cool. So then they have robot dancing in Times Square. And then there is the cat watching TV with a remote in hand. You can also see the hand is kind of scary, but super cool. A fluffy baby sloth with an orange knitted hat trying to figure out a laptop, close-up, highly detailed studio lighting, screen reflecting in its eyes. So we can see the prompt engineering culture perturbing all spheres of research. So here is the result. It's fairly fascinating. I'm not sure whether this is sloth or some very nasty demon, but it's cool nonetheless. And then they have the realistic category, like an artist brush painting on a canvas close-up, clownfish swimming through the coral leaf, a young couple walking in a heavy rain, horse drinking water. So all of these are very, very cool. And then there is a stylized category, I'm not sure why the spaceship is stylized, but okay, because it's an alien spaceship, I guess. So hyper-realistic spaceship landing on the Mars, an oil painting of a couple in formal evening wear going home get caught in a heavy downpour with umbrellas. You can see there is some artistic style here to it. You can also see a bunch of problems with the model, but considering this is the first one, and considering that also don't even have a text video data set, we'll soon see the details behind the paper. This is kind of fascinating. There is a table by a window with sunlight streaming through, illuminating a pile of books. So again, very cool. It looks like some type of a camera panning motion. Very nice. And then an emoji of a baby panda wearing a red hat. So we have the red hat, blue gloves. So you can see that there are no blue gloves actually. And then green shirt and blue pants. So again, some variable binding issues, but again, I will not complain because these results are truly fascinating. And considering that just this year we had DALL-E 2, and since then we had a Cambrian explosion of all of these models. So this is kind of fairly fascinating where we've come. They also can do, because of the interpolation module they have, which we'll see as soon as I open up the paper, they can do, they can animate a single image. So you can see here an image, and then you can literally create a video out of it. So here, a bunch of different ones. So again, you can see the sun kind of going through the body. So the model is having problems with the, well, common sense and just world understanding, which is expected considering how we're training these models. And then there is the turtle image here, and you can also just pair two images, like the source and the target image, and then you can do like a smooth interpolation between the two. So results look fairly cool. There is some like blur effect here, but yeah, super cool. And also you can just do video variation. So you pick a particular video, and then you generate a variety of similar videos. So this property, the make a video model, is inheriting pretty much from DALL-E 2, because as we'll soon see, it's leveraging DALL-E 2 model as the backbone. And yeah, let's maybe dig into the paper, and then we'll see those details. Okay, so let me open it up here. So the paper name is Make a Video, Text to Video Generation Without Text Video Data. And I guess that's a very important point here. So there is no text video data. So yeah, let's kind of then see how the thing works. So our intuition is simple. Learn what the world looks like and how it is described from paired text image data, and learn how the world moves. So learn how the world moves from unsupervised video footage, okay? So that's going to be kind of, they literally have a 3-stage approach. So if they first train the text to image model, which is going to be, as I said, some variation of DALL-E 2, then they basically train it on data sets of video data sets in an unsupervised fashion. And finally, they additionally fine-tune, they train this interpolation network, which we'll see in a couple of minutes. Okay, so as I said, it does not require paired text video data. That's kind of impressive. Okay, so let's see a quick remark here. So while there is a remarkable progress in the text to image generation, the progress of text to video generation lags behind, largely due to two main reasons. So the first one is the lack of large-scale data sets with high-quality text video pairs. I mentioned this multiple times, and some of the previous work, such as Cog Video, are using text video datasets, but to the best of my knowledge, they are super small, and that's the reason why they did not achieve any significant results yet. And then the second point they make here, and the complexity of modeling higher dimensional video data. So again, it's very compute intensive to do anything with videos. So those are two of the reasons why we didn't have any Cambrian explosion when it comes to text to video models as opposed to text to image. Okay, guys. So here's the high-level architecture. I'm just gonna first just give you some high-level overview, and then I'm gonna go through the experiments, and then I'll later get back and dig a bit deeper into how this thing works. So I want you to first recognize some components that are same as in the DALL-E 2 model. So if you haven't watched any of the DALL-E 2 explanation videos, because I haven't created one, I'm gonna give you a brief explanation how the model works. But for now, let's just kind of identify some components. So first we have input text here on the left-hand side. You can see a person doing yoga outdoor during a sunrise. And so what you do is you basically convert that using a clip text encoder into a text embedding, and then using this prior network, which is implemented as a diffusion model usually, then you end up with some image encoding. That's going to, well, because it's trained by the clip in the background, it's going to have all of the properties of clip image embeddings. And then you use that clip image embedding to condition the diffusion model that's going to generate. So initially, just ignore, for the sake of argument for now, just ignore the temporal dimension. Just assume we have a single image here. That's going to be the way they first train it. And so this is going to be a 64 times 64 like generated image from a diffusion model. Okay. Then initially they don't have this frame interpolation network. They just have additionally two super resolution models that do, this one will do 256, 256. So from 64, 64 to 256 256 resolution, and finally 768 or something. So yeah, so here you can see 768. And then after they've done that, after they train the model in the DALL-E 2 fashion, what they then do is they extend these architectures, the UNets of these architectures, such that they can also integrate the temporal information. Then they train that whole system on the video dataset without any labels. And finally, they train this interpolation, frame interpolation module using this masking of frames. Again, we'll see the details, but that's kind of the rough idea. The model thus learns not only the spatial structure of the natural images that the model was trained on, it also learns how to model the time, how the objects are morphing from frame to frame. That's kind of high level intuition behind the thing. But yeah, that's it. That's how it works. The 3-stage approach, I would say. And let's quickly see the results, and then I'll get back to these details behind the model. So let's just kind of skim the results. So you can see on this MSR VTT benchmark, which is a video benchmark proposed by previous baselines. I think Cog Video and other baselines introduced it. You can see that Make a Video basically like heavily outperforms them across these two metrics. So FID is way lower, and also ClipSim is way higher. So ClipSim, by the way, what it does is, so once you generate the video, you basically take the frames and you see how similar that frame is to the input text prompt that was used to generate that video. So how you compute the similarity is simply a dot product between the image embedding of the frame and text embedding of the prompt, and then you just find the dot product, that's the similarity, and then what you do is you do average across all of the frames, and that's how you get the ClipSim metric. To the best of my knowledge, that's how it works. One thing worth mentioning is because Make a Video uses clip in the background, that might lead to us overestimating the actual number here, or vice versa, underestimating the numbers here, because these other baselines are not leveraging clip, and thus it might be that this number is not that maybe accurate as this one here. So this one is kind of showing already that the model is way better compared to the baselines. Cool. Let's continue here. A couple more results. They also tested on this UCF 101 in zero shot and fine tuning setting, and again it outperforms the Cog Video, which was, I think, either trained or fine-tuned on UCF 101 training data set, and it still outperforms it. So that's kind of fascinating, even though Make a Video did not use images from UCF. So now I'm not sure about the overlap between Lion, which they are using for training Make a Video, and UCF 101. So there might be some data pollution there, but if not, then these results are super fascinating. And also you can see in the fine-tuning approach, Make a Video again just outperforms all of the baselines heavily. Okay, guys, and then what they do additionally is they do human evaluation. So they give they have these humans on the Amazon Mechanical Turk, and basically what they do is they show side by side. Here is a video from one model, from our model from Make a Video, and then the model from the baseline, and they ask which one is higher quality. And if it's 50, then they're kind of pretty much similar or the same. So you can see here it's always like above 50. So that means this Make a Video is way better, even in these human eval experiments. The faithfulness column basically tells you, they ask those reviewers to basically judge how nicely is the generated video described by the text that was used to generate it, and that's the faithfulness metric. And again, they're comparing both videos side by side. Okay, guys. So finally, before I dig into the details of the model implementation a bit deeper, let me show you a couple more results. So here's again the comparison between VDM, so the video diffusion models on the top. We have Cog Video in the middle, and we have the Make a Video on the bottom. And you can again see that the two baselines here are kind of way more abstract and blurry. If you zoom in here, the grass doesn't have all of the texture information and the details, whereas this one looks way better. Just eyeballing it does look better compared to the baselines. Then they showcased, again, from a static image, they generate an animated video. That's kind of cool. They here show interpolation. So this is the target image, this is the source image, and they basically show how they can interpolate very nicely between those images, whereas some of the baselines, such as film, is struggling with understanding like some concepts like that human hands are not supposed to break all of a sudden when you're interpolating between the images. So it does lack some of the world knowledge, and you can see that on the other hand, this model, the Make a Video, is managing to model the I guess temporal, has some temporal consistency and understanding, I guess. Cool. And finally, video variation. We already saw actual videos on their landing page, so I'm gonna skip that one, but it's very, very nice to have. Okay. Final thing they mentioned here, some of the downsides of the fact how they train the model, and that's that they are only using static images and text descriptions. Because of that, let me read this for you. So as discussed earlier, our approach cannot learn associations between text and phenomena that can only be inferred in videos. So how to incorporate these, along with generating longer videos with multiple scenes and events depicting more detailed stories, is left for future work. And obviously the reason for that is because they do not have a video text dataset. Again, mentioning that. So yeah, things like generating a video of a person waving their hand left to right or right to left, the model cannot do that reliably, because obviously static images, you cannot learn that from a static image. Okay guys, let's now see how the model works in a bit more detail. And ultimately, the first thing you have to understand is how DALL-E 2 works. So let me try and digest it. Obviously it's going to be hard to explain it in a couple of minutes. And I'm going to refer you to some of my previous videos, but yeah, stick with me. Okay, so there is roughly two stages of how you train DALL-E 2. So the first one is train clip. And for those of you who are not familiar with clip, I already covered the paper, and I've also done a code walkthrough of the original OpenAI's repo, so you can check out those videos if you want to know a bit more detail about clip. But on a very high level, what clip does is it learns this very rich joint embedding space between images and text, such that you have this cool property where you grab a piece of text, such as a corgi playing a flame-throwing trumpet. You basically embed it using a text encoder. You get this embedding text vector. And then if you do the same thing for some set of images, and you do basically a dot product, so you calculate the similarity between those vectors, you'll find that the highest similarity is exactly for those images which are best described by the text, as decided by human beings. So basically you can see here, there will be a very high similarity between this image and this piece of text. But if I gave you an image of like a car, and if I embedded the image of a car into this vector, then the dot product, so the similarity between that vector and this particular text would be, the similarity would be way lower. And that's a nice property that clip gives us. Okay, so once you have the clip, and hopefully you already knew how clip works, but yeah, and if not, hopefully that short description helped you. Okay, so then the next step is to basically train this model called the prior. And you can see that in the original paper, OpenAI tried a couple of different model architectures, not architectures, so basically generative models. So one is the autoregressive model here, and the second one is the diffusion model here. And they ended up using diffusion because it gave better results. Surprise, surprise. Okay, so what prior does, it learns how to, given a particular text embedding vector, it learns a set of plausible image embedding vectors as basically decided by clip. So let me kind of dissect what I mean by that. Let me read this passage here. It's kind of important. So for the diffusion prior, we train a decoder only transformer. So let me first break here. Let me stop here because it's decoder only. So if you are familiar with diffusion models, you've mostly seen UNet models. So the reason they're not using UNet here is because we are not trying to generate an image. We're trying to generate an embedding vector. And so because of because of the nature of the input and output of this prior, and that's that we have a text embedding vector here and image embedding vector here, they're not using an UNet, and instead they're using a decoder only transformer. Okay, so let's continue now. So we train a decoder-only transformer with a causal attention mask on a sequence consisting of, in order, the encoded text, so it's going to be the BPE encoded text, the clip text embedding, so that's going to be this thing here, and embedding for the diffusion time step. So again, that's like just the T and then embedded into some multi-dimensional space. And then the noised clip image embedding, okay, so it's going to be the noisy version of this one, and that corresponds directly to how when you're training diffusion models on images, you pass in the noisy image. So here you pass in the noisy image embedding vector, okay? And finally, a final embedding whose output from the transformer is used to predict the unnoised clip image embedding. Okay, so that's the idea. You're kind of training it. Let me try and draw that, but hopefully that was clear. So you kind of have a decoder-only transformer here, and you pass all of those different components, which I'm not going to repeat again, but like you have a bunch of these components, like text embeddings, blah, 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 and then ultimately you have this final embedding, and on top of it, you'll be generating the unnoised version of the image embedding. Now, important thing to understand here is that the ground truth is provided by the previously trained clip model. So let's assume this is the this is the text embedding from clip. Then this is the image embedding of that text image pair. So these two are connected. This is like the ground truth as provided by clip. And because of this, it's going to learn reasonable image embeddings given a text embedding. And thus learn the prior behind the clip model, if that makes sense. Okay, so why it's called prior is because given a text embedding vector, it's going to basically generate some plausible set of image embedding vectors, and obviously because of the stochastic nature of diffusion models, every time it'll generate a bit different image embedding vector, but it's going to be well centered around some mean of that output distribution. That's why it's called like a prior. It's setting a prior across the possible meaningful image embeddings given that particular text embedding. Okay, hopefully that makes sense. So once you have that, then you train a decoder, which is also, as you can see by the diagram, so when you see these kind of dots, these circles, that's a diffusion model. And so what you then do is you, again, now you have your regular diffusion model training, you pass in the noisy image and you try to denoise it, and you just additionally condition that model throughout that process using this particular image embedding, okay? And by doing that later on, when you pass a purely noisy image and a particular image embedding, that diffusion model is going to generate something that roughly corresponds to that particular image embedding. Okay, hopefully that makes sense. And that's how clip works in a nutshell. There is a couple more details. Obviously, there is like 2 additional super resolution models because this is going to generate like a 64 by 64 image, and then you need to kind of upscale it to bigger resolutions. Again, just to recap on a high level, what you now do if you want to generate an image in DALL-E 2 is you grab a piece of text, you embed it into the this text embedding, then you pass the text embedding into the prior. Prior is gonna generate a reasonable image embedding, and then you use that image embedding and you pass in a noisy image into the diffusion model to generate the 64 by 64 image, and then you basically upscale it 2 times using the super resolution models. That's it on a high level. I'm not gonna go any deeper than that. Okay. So now the question is, how do we get the temporal part? So how do we now generate videos? And the idea is to expand the convolutions and attention layers such that they can integrate the temporal information additionally, okay? So let me slowly start digging into those details. So first, just to recap the DALL-E 2 part. So they say here, prior to the addition of the temporal components, we trained the backbone of our method, a T2I, so a text-to-image model, trained on text-image pairs, sharing the core components with the work of Ramesh et al. So that's the DALL-E 2 paper authors, okay? And there is a couple components, as I said, prior network P, a decoder network D, and 2 super resolution networks SRL and H, like standing for, I guess, low res and high res. Okay guys, so now let's see how the temporal piece comes into the picture. They say here, in order to expand the 2-dimensional conditional network into the temporal dimension, we modify the two key building blocks that now require not just spatial but also temporal dimensions in order to generate videos. So convolutional layers and attention layers. Outer layers, like fully connected, don't have to be modified. Okay, and then they say temporal modifications are made in most UNet-based diffusion networks. So that means they have to modify the spatio-temporal decoder, DT, that is now generating 16 RGB frames. Okay, so we are starting from a diffusion model that was generating a single RGB 64 by 64 image here, and we are extending it to generate 16 RGB frames, okay? We're gonna see the details of how that works in a second. And then not only that, but they also say they also modified the newly added frame interpolation network, this upper arrow F, denoted as upper arrow F, increasing the effective frame rate by interpolating between the 16 generated frames as depicted in figure 2. So, and finally the super resolution network. So all of those will need to be modified. They say this part, so interpolating between the 16 generated frames, so you can see that it's going to have this masking logic where it's going to try to infer what should be generated in those black frames, and by doing that you can do either interpolation or like extrapolation of your generated 16 frame video. That's going to be the thing with this interpolation network. Okay. So they say a couple more details for the super resolution module. So this SRL, so the low res module, operates across spatial and temporal dimensions. In qualitative inspection, we found this to significantly outperform per frame super resolution, where you don't model the temporal information. It is challenging to extend the SRH, so the high-res network, to the temporal dimension due to memory and compute constraints, as well as the scarcity of high-resolution video data. So SRH operates only along the spatial dimensions, but to encourage consistent detail hallucination across frames, we use the same noise initialization for each frame. Okay, so that's why they have, in this picture here, you can see that this is kind of denoted like fixed noise, because this one is only doing frame. You're literally doing you're using the same model and just doing the upscaling, whereas this one is also actually has the temporal information integrated into the architecture. Okay, that out of the way, let's just continue slowly and try and digest what's going on. Okay, let's see how they create these pseudo 3D convolutional layers. So because regular 3D layers are very compute intensive, they opt on the side of using this pseudo 3D. And it's very, if you're familiar with the concept of depthwise separable convolutions, this does a very similar thing. So you first do spatial processing and then you do the temporal processing. So you kind of decouple those as opposed to doing a joint processing of both of those, okay? So it's one of the reasons for not using the 3D computational load. And then the second reason they say is, well, they want to retain the previously learned spatial knowledge in the spatial convolutions weights, right? So because you first trained on the image text pairs, you want to retain those weights and just start from there. And that's what they do. They literally do identity. They initialize the network initially using the identity function, and because of that, initially it's behaving as if you had 16 independent 2D diffusion models. Okay, so here is how the process roughly looks like. You grab the input tensor, which is BCFHW, because you have C number of channels, and this is the image spatial extent, number of frames, and batch dimension. And so what they do is they first apply 2D, so it's going to be apply a spatial processing of the frames, and after that they do transpose operation, which is going to lead to them processing the temporal dimension now. So that's when they apply the com1D, and I think it should be 2D here as well, but they're just doing like 1 times 1 2D convolution basically. So yeah, and then finally they also apply the transpose operation so that they get back into this canonical shape here. Okay, and as I previously mentioned, note that at initialization the network will generate k different images due to random noise, each faithful to the input text but lacking any temporal coherence. So let me explain why that is. To understand that, we need to check out this image here. Okay, so here is how this is implemented. So we first do the spatial processing. So you can just treat these as like 3 independent diffusion models, even though they are not, but like for the sake of argument. So you first process the spatial information, and then you can see here the way they initialize these temporal filters is that you can see 1 here and then zeros here, and because of that you will basically end up just copy pasting the output, so these feature maps, to the next stage. So initially, because these are initialized the way they are, you'll just end up copy pasting these feature maps. You'll just copy paste this feature map forward, and then you'll continue on your processing. And because of that, you literally have 16 independent diffusion models that are going to generate 16 images that correspond to the text prompt, but they are very different from each other, and there is no temporal consistency. Okay. Temporal consistency will be later learned using the unlabeled video dataset. We'll get there a bit later. Okay, so that's the first part. Hopefully that kind of makes sense. And then they have to do the same thing for the attention layers. Very similarly, you can see here they first basically do some flattening such that we have H times W tokens. Then they apply the attention, which is going to be like a basically complete attention pattern. Every token is going to attend everything, every other spatial token. Then they do transpose. That's going to allow us to process to do the same thing for the temporal extent. And then again they do transpose such that we are back in the canonical shape, and then unflatten is going to return this into H times W, if that makes sense. Okay, and they say similarly to conv P3D, P standing for pseudo, to allow for smooth spatio-temporal initialization, the attention 2D layer is initialized from the pre-trained T2I model, and the attention 1D layer is initialized as the identity function initially. Okay, so let's again see the diagram here. The diagrams are quite vague, and also the code is not released, so I couldn't go and dig into the code and understand some of the details that are kind of ambiguous or not clear enough from the paper. But yeah, I'll do the best I can to infer the correct mechanisms here. So we first have the spatial attention. So you do the spatial attention, and then you can see that this temporal attention, because of the way this is initialized, there are all zeros here, and because of the fact we have a skipped connection, that basically means that initially it's behaving as if there is no temporal modules being added. And because of that, they preserve the identity, the equivalence with the text to image model. So the parts that are kind of confusing is like nothing is labeled, like I don't see any dimensions being denoted here, like embedded image tokens. I'm not sure what this is referring to. It's kind of vague, to be honest. I'm not sure whether I'll be able to reconstruct the paper from just the information that they have here. So yeah. Okay guys, let's continue here. There is only a couple more paragraphs worth explaining here. So let's focus on this frame interpolation network. Okay, so let's kind of read this. In addition to the spatio-temporal modifications discussed in the previous section, we train a new masked frame interpolation and extrapolation network, arrow up F, capable of increasing the number of frames of the generated video either by frame interpolation for a smoother generated video or by pre-post frame extrapolation for extending the video length. Okay, so in order to increase the frame rate within memory and compute constraints, we fine-tune a spatio-temporal decoder on the task of masked frame interpolation by zero-padding the masked input frames, enabling video upsampling. Okay, so this is again where the three-stage approach kicks in. So they first train this spatio-temporal decoder DT using the unlabeled, the unsupervised video dataset, and then they use it to fine-tune this particular model. So they mentioned then here, when fine-tuning on masked frame interpolation, we add an additional 4 channels to the input of the UNet. 3 channels for the RGB masked video input, and an additional binary channel indicating which frames are masked. Okay, so these 3 channels I guess make sense, although this is kind of in discrepancy to the drawing they have up here, because this kind of makes you think that they always completely zero out the frames. And what this is kind of telling me is that they just have additional flexibility of having an arbitrary patch inside of the image being masked out instead. So let me just go back here again. So they have these 4 channels, so 3 channels for the RGB blah blah blah. So that basically means the following. So you can literally grab those 3 frames. So let's take one of them, like maybe one that corresponds to our channel, like the red channel, and then you can literally mask out only a particular part of the image, and then force the interpolation network to learn what should be inside there. Okay, so whereas the diagram up there shows that they're constantly zeroing out the whole frames. But the part that's kind of confusing to me is this binary channel indicating which frames are masked. So that kind of alludes that those are either all ones or all zeros, depending on whether we want to infer on whether that image is masked or not. But that's kind of confusing because obviously for the images where you don't want to do any masking, you just don't do the masking, and then those 3 channels should have enough information. So I'm not sure why the 4th channel, that's kind of confusing. If anyone knows why, feel free to comment down below. Okay, so then they say we fine tune with variable frame skips and FPS, so the frame per second conditioning, to enable multiple temporal upsample rates at inference time. Okay, so we denote blah 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 as the operator that expands the given video tensor to mask frame interpolation. Okay, for all our experiments we applied this interpolation network with frame skip 5 to upsample a 16 frame video to 76 frames. So here they're referring to just the eval we've seen previously, where they always expand to this exact frame size, but like in general during the training they allow for additional flexibility by, as you can see here, by changing the frame skips and the FPS. They don't have to always extrapolate to this particular number of frames. So what this basically means is that what they do is they grab an image, and then they have 4 images here that are going to be masked out. So these are just going to be masked out, and then they have an image again, and etc., etc. And because they have in total 16 of the frames, you can count that you'll have 15 of these, right? You'll have 15 of these, and then the last one ends here. So it's going to be 15 times 5 plus the last one, plus 1. And that's why they end up with 76. Okay, so that's kind of how they do it for the eval. They kind of have these 4 here, and then they infer what's going on in those frames. And because of the way how the decoder was trained, you'll have the temporal consistency built in. Okay, let's see a couple more details, and then I'm going to try and make a high-level overview of what's going on. So the different components of make a video described above are trained independently. Okay, that's very important. So the only component that receives text as input is the prior P. We train it on paired text image data and do not fine-tune it on videos. The decoder, prior, and 2 super resolution components are first trained on images alone, no aligned text. Recall that the decoder receives clip image embeddings as input, and the super resolution components receive downsample images as input during training. Okay, so that's the DALL-E 2 part. Okay, and now comes the second and the third stage. So after training on images, we add and initialize the new temporal layers and fine-tune them over unlabeled video data. 16 frames are sampled from the original video with random FPS ranging from 1 to 30. We use beta function for sampling, and while training the decoder, start from higher FPS ranges, which is less motion because you're taking frames with a very small temporal delta, and then transition to lower FPS. So that means you're now gonna be sampling with a lot more space time-wise, so with a bigger time delta between those frames, and thus you'll have more motion naturally. Okay. And finally, the masked frame interpolation component is fine-tuned from the temporal decoder. Okay, that was a mouthful. Let me try and explain this part with the video. So let's go back to the diagram above here. So how I understood it is that because now they don't have the text video dataset. Because of that, what they do is they grab a video and then they sample 16 frames. And they also have this curriculum learning where they initially just have this sample with a very small temporal delta, and then they later have bigger and bigger temporal delta. So that's kind of a form of a curriculum learning. So once you have those 16 images, because you don't have the text, what you do is you just embed them using the image encoder of the clip, you get the image embeddings, and then you literally now use those image embeddings to condition this temporal diffusion model, right? So hopefully that makes sense. So now you're gonna do the same logic. You start from a noisy image, you condition each of these 16 diffusion models with those particular image embeddings that corresponds to particular frames, and then you train it in such a fashion. So because there is this temporal integration, they're not really 16 independent models, but you can kind of think about it that way, because you will provide them with 16 image embeddings. So once you train that model, the spatiotemporal decoder, in that diffusion fashion, then in the third stage of the training, you grab those and you train this frame interpolation network, where you'll occasionally be masking out. Well, here it looks like it's like whole frame, but like looking at their description previously with the 4 additional channels, it seems they are just doing also partial zeroing out of the frames. Now the part here that's confusing to me is how do you condition the black frames, right? Because in the inference time, you're obviously trying to generate something that does not exist, so you do not have any conditioning signal. So that means you won't have it here either. So I'm not sure how they handle, there is no explanation whatsoever of how this is exactly done in the paper. What they might be doing is some form of just MSC loss or something, or simply unconditional generation. And because during training you actually have the ground truth images, you can use some form of like MSC or something to just make sure that whatever is generated is closer to the output. Again, confusing, that doesn't make complete sense. I am still confused a bit by this. If anyone has any hypothesis, feel free to just comment down below. I'd be very happy to read through and discuss what's going on here. In any case, guys, that's it. Let me again just show you quickly the videos. They are fairly impressive. I love this one with the doggo. It's a dog wearing a superhero outfit with red cape flying through the sky. And with that, I'm gonna leave you here. Hopefully you took out something from this video, you learned something new. If you did, consider subscribing to this channel, share the video out, and until next time, bye bye guys.